Okay, everybody, we're back. Apparently, I ran into memory issues with my computer, and that video ended just as I was finishing up this line here. So, we're collecting all these terms, and I'm going to take the minus 12 to the other side, and that simply becomes 12 volts. Okay, and that is our first equation. Okay, we've got that one out of the way. Now, let's go to our next loop. So we're going to sum the voltages for loop 2. So we have a minus I1 times this resistor right here, minus because I1 is going down, I2 is going up, and since we're in the second loop, everything is in reference to this loop. So I1 is now minus times that 3 ohm resistor. Then we add the loop we're looking at, and we have a 3 ohm, a 5 ohm, and a 6 ohm resistor, and that makes a total of 14 ohms. Then we have an I3 term, which is working against I2, so it's minus times 6 ohms. Then we have an I4 term, but it does not touch anything that is common to the second loops. That's just 0. There are no voltage supplies in here, so no constants, and basically we have our second equation. Then we go to our third loop. We'll sum the voltages for that third loop. That's not a very good looking sigma. We'll have to live with it, I guess. I1 does not touch that third loop. I2 does. It's working against I3, so we subtract it. And then we add our I3 loop term. We have a 6 and a 6, and nothing here, so it's just 6 plus 6 is 12. And then we have an I4 term here. It touches the I3 loop, but we see here between the two of them we have 0 ohms. So we just put that 0 ohm term in there. And again, there are no voltage sources in there, so that just equals 0. So that's our third equation. Then we've got our fourth loop that we're going to sum the voltages to find that current. I1 does not touch it, neither does I2. I3 touches it, but again there's no resistance. It's just 0 ohms between this loop and that loop, so that's just a 0. And then we add our fourth term in there for the fourth loop, and we have a 7 and a 6, which makes 13 ohms. Again, no voltage supply is in there, so that just gives us another 0. So we have 1, 2, 3, 4 loops and 1, 2, 3, 4 equations. This is our fourth one, and there's our first one. And so let's develop our matrix system. So now we have an I1, an I2, an I3, and an I4. And I was working this, I realized that some of you may have calculators that do not go up to 4x4 matrix. I promised we wouldn't do that. We'll definitely not do that on an exam, but you know, this isn't a homework problem, so this is still a good exercise for you to follow through for a larger matrix. Now we need to collect all of these constant terms, and so we got here for that first time we have a 9, then we have a minus 3, we have a 0 and a 0 and a 12. Then for the second equation we have a minus 3, a 14, a minus 6, a 0, and a 0. For the third term here we have a 0, minus 6, 12, 0, and 0. Then for our fourth term here, we have 0, 0, 0, 13, and 0. So there, we have our four equations, our matrix set up. I didn't do a very good job of getting my numbers here into a column, but we will live with that. Okay, so now that we've got our matrices set up, I'll go ahead and use my HP calculator here. If I can remember which buttons to push. And so we've got a matrix here now that is 4 by 4. We'll go ahead and just start at that first term. We have a 9, then a negative 3. Oops. Now a negative 3. There. 9, negative 3, 0, and 0. Sorry about my computer being so noisy. Okay, so you have 9 minus 3, 0, 0, minus 3, 14, minus 6, 0, 0 minus 6, 12, 0, 0, 0, 0, 13. Okay. And then we go to our constant vector. We've got a 12, a 0, a 0, and a 0. And so there's our first matrix. I want to go ahead and take the inverse of that. Get our second matrix, multiply them together, and now I have some answers. I1 equals 1.467 amps. I2 equals 0.4 amps. I3 equals 0.2 amps, and I4 equals 0 amps. And let's see if that makes any sense. So we go back here and look at our circuit. We got a value for I1 and I2 and I3, and I4 came out to 0. Does that make sense? And it does, because we have a short circuit right here. You know, we have current coming into that node, and will any go that way? And the answer to that is no, not likely, because we have a short circuit here, so this part out here doesn't affect that Norton circuit value, because we are shorting through here. So yeah, I would expect that fourth term to indeed come out to 0 amps. Okay, so now we ask, what is that Norton current? Well, normally I'd say it's I3 minus I4. But since I4 is 0, the Norton current in this case is just I3. So I Norton, which equals that short circuit current, is just simply equal to I3. So I Norton equals 0.2 amps. So we have that for our Norton current, and we saw that V Thevenin was 2.088 volts. Well, that leaves us one other value to find, and that is our R Thevenin, which is equal to R Norton. And so, which is equal to our V Thevenin divided by our I Norton current. So, let me just do V Thevenin, which is 2.088 volts, divided by 0.2 amps. And we get R Thevenin which is equal to R Norton, is equal to 10.44 ohms. So we have our three critical values for our Thevenin and Norton circuit. Are we finished? Not quite. So, first of all, let's draw our Thevenin circuit. Thevenin circuit would be the Thevenin voltage, which is 2.088 volts, with our Thevenin resistance, which is 10.44 ohms, with our load resistor put back into the circuit, and whatever it is, we didn't worry about it because that's not important as far as finding the Thevenin circuit is concerned. So there's our Thevenin circuit. Now we want our Norton circuit. I got a positive value for the current, so I'm going to point it up, and that's 0.2 amps. Here's our load resistor. And the Norton circuit, the Norton resistance goes in parallel, so that's at 10.44 ohms. And there we have it. We have a Thevenin and a Norton circuit. Circuit that gives us our open circuit voltage, and a circuit that gives us short circuit current. The maximum current available to that load resistance, the maximum voltage available to that load resistance is given by this circuit, and this circuit likewise for the current. Okay, that concludes the lecture portion. Now, as I promised, we've got a quiz. And I have two questions for you, and all I want you to do is reply back to me in an email your first answer, which is either A, B, C, D, and then your second answer, which is either A, B, C, D. And then the first question is, in performing a Thevenin analysis of a circuit, what is it that we're looking for? We're looking for a short circuit current, a short circuit voltage, an open circuit voltage, or an open circuit current. Tell me which answer is correct. And then the second equation, or second question, in performing a Norton analysis of a circuit, you are looking for a short circuit current, a short circuit voltage, an open circuit voltage, or an open circuit current. Which one of these are we looking for? Hopefully you paid attention in today's lecture. And I realize this probably is not the most exciting format, and I'm hoping I didn't go much past the 50-minute time slot. Again, make sure you email me with any questions, whether it's regarding the lecture, the homework, or things that we'll be doing to finish out the semester. I hope you have a good day, and keep in contact with me, please.